This next part just shows a cathode ray tube and how it relates to J.J. Thomson's discovery that atoms were divisible.
So today I'm at the University of Sydney with Dr. Phil Dooley, and we're talking about how our idea of the atom changed from a tiny little hard sphere to something more complicated. And this apparatus has something to do with that.
Exactly. It was quite a landmark historical experiment. It's just made of a tube of glass connected to a vacuum pump, and in the tube of glass there are two pieces of metal connected to a high voltage power supply.
So we can suck the air out of here.
That's right.
And then apply high voltage to two metal plates.
Yes.
Okay.
Normally with high voltage in air, we don't get anything except maybe a big spark. But what Geisler found, who did this in 1857, was something quite different. So shall we have a look?
Let's do it.
Okay, let's turn on the pump and the high volts. Turn off the lights so we can see what's going on. As you can see, something's happening now.
Yeah, I see a bit of a pink glow in there.
That's right. So imagine Geisler, the first person to ever see this. It's pretty surprising. That started people thinking, what is this stuff that's coming from the cathode? It seemed to be a ray emitted from this negatively charged one, which they called the cathodes, therefore it's called a cathode ray, and it became the topic for research for the next 40 years as all the big wigs of physics and science basically tried to work out what was going on.
So what did they figure out? I mean, what is going on? What's producing this glow here?
There were two main camps. One thought that it was waves, and the second thought that the electricity was being carried by a stream of charged particles. Over the next 40 years, they basically came to the conclusion, well, it was J.J. Thomson in 1897 who came up with the idea that there is a stream of very small charged particles, negatively charged. They're smaller than an atom. So the smallest atom, hydrogen atom, they're about 1,000th of the size of that. And it doesn't matter what material the metal is, it's always the same particle. So this particle appears to be in everything. This electron, as it was known, is what's carrying the electricity.
So Thomson came to the conclusion that all atoms have this particle as one of their constituents.
That's right. So it wasn't a billiard ball. There had to be something inside the billiard ball.
So how do I picture like a billiard ball with bits inside it? I mean,
well, you should probably think about a pudding.
A pudding?
Yeah, well, that's what his idea was, that it was a plum pudding, very dear to...
And the next slide just talks about his plum pudding idea.
So the word atom means uncuttable.
That's right.
So the Greeks were thinking of it as a tiny hard sphere.
That's right.
And even up into the 1800s, that was the idea of an atom. The smallest piece of matter, tiny hard sphere.
Yep.
But then we find out that that's not quite right.
Not quite. There were experiments in the 1800s that discovered the electron. J.J. Thomson's experiments really worked out the electron was smaller than an atom, about 1,000 times smaller than the hydrogen atom.
And it was in all atoms.
That's right, not just hydrogen. Whatever material he did his experiments on, he found there are electrons in them.
There are electrons in all atoms. So I guess when you find something that's smaller than an atom, you need to propose a new model for the atom that actually has something smaller in it, some substructure.
That's right. So, something like this.
This is our model of the atom.
This is our model of the... In his day, it was known as the plum pudding model, but here we have...
Cherry tart.
Cherry tart, okay. So, but the idea being that we have an overall atom, usually pictured as spherical rather than 2D, but embedded within it, this is the important part, there are negative electrons represented by cherries, and they can come out. The overall atom is neutral, so that means the pudding part must be positive.
Now, how would you get one of these electrons out of our pudding here?
So electrons are negatively charged, so we'll need to put something very positive, which attracts electrons, a high voltage.
And that would have the effect of, say, like, plucking a cherry out of the pudding.
That's pretty much it. Yep, you could do it kind of like that.
So we're
So after that, then what happened was we have the Rutherford experiment, which is kind of where they're leaving off with atomic theory. So Rutherford, let's see. I don't know why this is bigger. Sorry. Rutherford worked for Thomson, and he actually agreed with Thomson's model and actually was trying to come up with an experiment to basically verify Thomson's model of the atom. Unfortunately, his experiment actually kind of like complicated things and actually ended up disproving Thomson's theory. But basically, he was trying to confirm Thomson's model. Um, Rutherford is also responsible. He actually discovered alpha and beta radiation. So in his experiment, he actually used alpha particles. And the reason why it's important that he used alpha particles is because they're positive. So it's kind of an ingenious way that he set up his experiment. So right here, what they have is they have the radioactive sample, and the radioactive sample is what is releasing the alpha particles. They had a lead box around it just to basically so that the alpha particles couldn't go anywhere except where they wanted them to go. They had a piece of gold foil, which was exceptionally thin. It was hammered to a couple atoms of thickness. And then they had a fluorescent screen around it, so like it actually had like phosphorescence. So when an alpha particle hit it, it actually would light up so he could see where the particles were hitting. So what they thought was with the Thomson's model was that there was the kind of the negative charges were spread out. So we thought that they would either kind of just pass right through or have a slight deflection. And again, this was set up to actually prove Thomson's model correct. So when they did the experiment, what they said, they thought it was just going to go right through. So you can see down here, he kind of thought that the alpha particles weren't really going to hit anything and kind of just move right through. The thing that was like the discrepant event, the thing that was like the moment for Rutherford was that some of the particles came back at very high angles, which was unexpected. And I mean, it wasn't like in one day. He repeated the experiment many times. And again, like the interesting thing about science is you have as much information as you have. You come up with an experiment, you kind of have an idea of how you think it's going to go, and then the big thing of science is like, what do you do when it doesn't go the way you think it's going to go? So what happened for Rutherford is he repeated the experiment, he kept finding the same results, and what he ended up saying was the only thing that explained these particles that came back at the really high angles was that there had to be something in the middle of the atom that had like a lot of positive charge, which was making that very large deflection. So, I mean, Rutherford basically discovered the nucleus. But again, they didn't know that the nucleus existed. He didn't expect the nucleus to exist. It kind of just happened because of like this discrepant event. So remember, sometimes discrepant events are good. So what he said is 98% of the alpha particles went straight through, which is what he expected. The thing that was weird was the 2%, where it had the large angles. And the really weird thing that he has a famous quote for is about 0.01% of the alpha particles actually bounce back at the radioactive source. And his famous line was, it would be like if you took a shotgun and you shot it at a piece of tissue paper and the bullet bounced back. It was just very unexpected, and which is what kind of made them think that there had to be something in the atom that had this large positive charge for it. So like we said, his conclusions were that the atom was mostly empty space, and the reason why is because most of the alpha particles went right through it. They didn't run into anything. That they're very dense particles, and they have the nucleus has this really small size but very large in mass. So it's kind of this discrepant thing itself. It contains over 99% of the mass, but it's like 0.01% of the actual volume of it. And the dense particle in the middle, the nucleus, was positively charged, which was, we now know, our protons and our neutrons. So just keep in mind, what he did was he said, okay, the plum pudding's out, and then what came about was the nuclear model because of that. So the last things for this one is we end up with a new nuclear model, and the atom contains that tiny dense center called the nucleus, and you can see it's just such a small area, but it contains so much of the mass. So the nucleus has essentially the entire mass of the atom. Obviously, electrons do have mass, but they're just so small that when you round with sig figs, you literally round them out. The nucleus is positive because it has the protons in it. And I apologize, I should have made this bigger when I did it. The electrons go around the space surrounding the nucleus, And the little check mark down below says like water droplets in a cloud, which I apologize are off the screen, but I can't unfortunately make it any bigger right now. This is just another summary of it. You can see, it contains 99.9% of the atom's mass. It's very positive. Most of the volume is that empty space. And again, even this nice little diagram right here, like, it is so not to scale. I mean, think about 99.9% of this, you wouldn't even see the nucleus because it's just so small comparatively. So again, even the scale of the model is not, good for it. So last thing we have is I'm leaving you with a couple practice problems, and then there's like one more video clip.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now, if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Oh, I'm so sorry. I don't know what happened with that. But that's where we'll leave it for right now.